Okay, hi year 13s. This is where we're going to start our topic on electrostatic forces. And this builds quite a lot on our topic on electric fields last year. So that's chapter 8 in the textbook if you want to have a look at that. I think it's starting from page 116. And what we'll need to do is use a lot of the ideas that we got in that topic to talk about this one. So this might look kind of familiar. We've got two charged plates. Okay, one is at some potential difference. So you can say one is at one is at x volts and the other is at negative x volts. So that means we've got a potential difference of 2x, okay? So PD equals 2x. What we've also got here is the actual distance between the plates. So we could maybe call that S, the separation. Sometimes you see it written as D, the distance in between them, okay? In fact, I think that's most often what they do. Anyway, what we also do conventionally is we represent the direction of the electric field in between them as going from positive to negative. Just made a small mistake there. I did the arrow there. They normally do it at the center, so it's clear that the direction of the field, rather than putting it down there where it just looks a little bit muddy. Now, one thing that I should be more careful to do is to draw the separation to be exactly the same. Because if you remember, the strength of the electric field is uniform at all points inside there if the plates are parallel, okay? So if plates parallel, the field is uniform. Okay. And one exam question which I've seen is it asks, okay, so what we've got is we're going to have an alpha particle being accelerated into this. So here we'll have an alpha particle. It's got 4 particles in total. Well, it consists of 4 particles in total. 2 of these and 2 of those. Hopefully you remember what an alpha particle is actually made from. If you don't, well, I'm about to tell you. It is made from 2 protons and 2 neutrons, giving rise to this mass number and this atomic number. From that, of course, we can also know its charge. If it had a net neutral charge, it would be a helium atom. So it's got a positive charge because those 2 protons, whichever ones you've chosen to be the proton. And so what we can say is, all right, so if we're going to fire it in here, so we give it a certain momentum at this point and we send it in here, what kind of path will it take? I'd like to have a think about that before I actually talk about it. But let's think about, okay, so what kind of path will it take? Now, of course, straight away we can say, well, it's got a positive charge, so it's going to be repelled from the positive side of this, and it's going to be attracted to the negative, okay? What we also assume conventionally is that this is in a vacuum, okay? So it's not going to be affected by air resistance. It doesn't get much affected by air resistance anyway because it is so small, even compared to many molecules of the air. So then what we think about, right, what kind of path would this look like? Would it look like, let me see, what color have I chosen? Let's go with green let's go with blue so we can see it. Would it go like this? And I'm sure you realize, no, probably won't do that, okay? Now the field is uniform, so it is going to experience a net force in this direction. But is that force going to change? The force itself isn't going to change, okay? But also the mass of the alpha particle isn't going to change. It's the acceleration. There will be a constant acceleration. So its path is more likely to look a bit like this, getting progressively steeper because it is accelerating. Something like this, okay? Of course, it depends on what the initial velocity of the alpha particle is, depends on what size this is and all that kind of thing. But what we should be seeing is that increasing gradient on it. Hopefully that's clear enough in the video. Anyway, what we want to think about sometimes is some of those key things from that last topic if we're talking about an electric field. So an electric field is defined as basically the force per unit charge. And that gives rise to the unit newtons per coulomb. It looks like a lowercase c, it should be a capital C. Okay. Another way of calculating it is E equals V over D. The electric field strength is the what am I trying to say here? The potential difference divided by the distance. Okay. So it's the same at all points. But the strength of the field is given by this thing D, which, I just had to remember what I was talking about for a sec there. So just don't confuse this with the idea that perhaps the field strength will get less as we go further through the field. Okay, this is uniform. Okay, And if you think about it in some way, it kind of makes sense, because if as I go further from this one, well, I get closer to that one, so that gives rise to this uniform field whenever the plates are parallel. Now, of course, it is not exactly uniform in any case, because even if you've got plates which are pretty well onto parallel, they're not going to be completely uniform themselves. They're not going to be completely smooth and this kind of thing. So we can definitely approximate a uniform field. And the idea of a uniform field is still very useful to us. Okay, although it's not the truth, we can never actually arrive exactly at the truth. So these models, these things are very useful because they help us to think and get close to the truth and do some worthwhile physics. Other things that we want to reflect on are the different charges and the way in which we actually represent them. So we may have a negative charge, and we may have let's just imagine these two are an infinite distance apart. So we'll just do our infinity symbol, and we've got a positive, so they're not going to affect each other. Okay. Now, of course, we don't need an infinite distance for them to be basically no effect, but that is the distance it should be at, because it is not a subtractive relationship. It's a multiplicative relationship, or we multiply by the inverse of the square of the distance between them. Anyway. We'll get onto that stuff later if you didn't hear what I was waffling about. Just remember, conventionally, we represent the field lines going from positive to negative, okay? So, like this. And again, we tend to write them like this. And we try to draw them at exactly, exactly along a radius of that. So, from positive to negative. Excuse the sloppy diagrams. But I prepared this before we knew we were going to be locked down. Okay, so that's just the kind of standard way in which we represent them. Now, with protons and electrons, we can treat them as little spheres, because basically protons are, electrons are points, and that's absolutely fine. We can still imagine this. It's kind of like a sphere, just a really, really infinitesimally small one. Okay, but let's think here about charges and spheres. Now, if we've got something which is geometrically slightly more complicated than a sphere, let's imagine we've got a charged object of some size, okay, and some shape. How we actually do the maths on locating where the charge is centered is much, much more complicated. So what we do is we don't really bother with those at this level, okay. What we tend to focus on is a charged sphere, okay, and let's say it's got a positive charge. Now, we don't know the exact distribution of those charges, but if it is a conductor, which is what we assume, we can regard all that charge as acting at a point at the geometric center of that object. Okay, so in this way, we can actually imagine it as a point, which makes the mathematics behind it a lot simpler. And it's also very, very useful as well, because we can use that simplification to make predictions and actually do some physics or do some engineering. Okay, so basically we can treat these as a sphere, as a point. Okay, so yeah, if we have a, let me see, the charge. No, that's pretty much it. So in that sort of way, we imagine here's a sphere and here's another sphere with a negative charge, and again we just imagine that the charges are all acting about that point there. Okay. Now, because of that, what we have got is we need to consider there may be a distance in between the actual spheres themselves, a distance of x. Okay. But if we're considering the charges acting about these points at the center, what we also need to consider is, let's imagine these are both the same size. Okay. Then the total distance between them, when we're thinking about those actual distances there, will be x plus 2r, because we're treating the charges as all acting about those points there. Okay, and if you think about it, it is kind of like the sort of main point for the charges on this thing. So yeah, we don't need to, so this is actually only useful when we're outside the sphere, by the way. And if we're actually inside the sphere, we do need to start considering the distribution of charge, which is usually a lot more complicated. Okay, so that is the actual distance that we use mathematically between them, not the actual physical distance in between them, but the distance between the centers. Okay, so Then we want to think about the actual forces and the charges. So let's think about the force. Now we need to think about some variables. What things can we consider in this case? Well, we consider the charges of the two objects. So let's just call this Q1 and let's call this Q2. And what we also want to think about is the distance in between them. Now it's an inverse square law. So what we can think about is the sort of the length of the actual circle, the radius of the actual circle formed from this to this and from this to this. So we can call that R. And let's think about what actually makes sense. If these are larger, then there should be a larger force in between them. By the way, we should have attractive forces in this case. Okay, so if these charges are larger, we should have a larger attractive force in between them. So we can maybe write Q1, and what actually happens is that they multiply together over multiplied by Q2, and of course it's an inverse square law. So if we double the distance, that means the actual strength of the force is divided by 4, okay, because it's an inverse square law, so over R squared. So what we can now say is the force is proportional to the product of the charges divided by R squared. But it's not quite as simple as this. It's not very difficult, but it's not quite as simple. So the constant of proportionality is Coulomb's constant. Now this is one you don't have to remember exactly, but you do have to remember the equation itself. So, well, effectively you do. So Coulomb's constant, the thing which actually relates the force with this here, is 1 over 4 pi epsilon 0 R squared. Oh, no, not R squared. 4 pi epsilon 0, the R squared is already there. Okay, that is Coulomb's constant. Okay, so 4 pi you're probably fairly familiar with, but what is this thing here, epsilon 0? Just a curly E. So this is what's called the permittivity of free space. So this is imagining a perfect vacuum, which we can approximate in certain labs. Permittivity, and it basically tells us how well the actual physical space that the universe consists of, how well it admits the electric field, or how well the electric field penetrates a vacuum. Okay, so you don't need to remember it. It is given to you in the data sheets, but it is 8.85 times 10 to the negative 12. I don't remember it. I've just read it off my computer screen. And the quantity is farads per meter. You don't need to know what a farad is just yet. We're going to do that stuff whenever we get on to our topic on, let me just make sure I'm still in shot here. Our topic on capacitors. Okay. Anyway, combine those and we get that equation. The force between two charges is equal to Q1, Q2, the product of the charges, divided by 4 pi epsilon 0 R squared. So I'll need to double check if that is actually given to you in the exam. I think that it is not, but epsilon 0 is given to you. Okay, but it sort of makes sense. You know, it makes sense that as you increase distance, you should get a decrease in the actual strength of the field. Now let's look at well, okay, yeah. So the next thing is, this is what is known as Coulomb's law. Okay, discovered by a French guy a very long time ago. Just kind of in the wake of Newton's discoveries. Now, this is useful because you will be given questions about forces in between charges. Okay, and what we want to think about also is, what if the charges are opposite in sign? Okay, so here we've got charges in opposite sign, right? How should we treat them mathematically? Because we've got the force is equal to, well, one of the charges is positive and the other charge is negative. So yeah, so Q2 is negative, Q1 is positive. So what we're going to get, let's just do a proportional sign over R squared. So what that means is, what we're going to get is a negative force. That sign just tells us what the force is actually doing, and it is the way I sort of remember it is that this force will give rise to a decrease in distance between them because they're going to be attracted together. And of course, that means, you've probably inferred already, if we've got, let's say, two charges which are of the same sign, so we've got two electrons, they're repelling one another, or two protons also repelling one another, that means we get a positive answer because, you know, multiply two negatives, we get a positive, multiply two positives, we get a positive. Check I'm still in shot. Good. Okay, so that's just one thing we need to be very careful of when we're doing calculations with this, is actually using our variables, our signs correctly. Okay. Now let me see. Let's do a work example on this. Okay. So I've got two spheres. We've got one sphere which is a charge of negative 0.4 coulombs, another which is positive 0.7 coulombs, and they are placed 12 centimeters apart. Okay, let's say that's 12 centimeters. Okay, 12 centimeters, and they've each got radius of, let's say, 1.5 centimeters. Okay, so R equals 1.5 centimeters. Okay, so what we want to do is calculate the force between them due to the electric field. So let's look at our data. So we've got Q1, doesn't matter which one we call Q1, we'll just do it from left to right. Negative 0.4, Q2 equals 0.7, put the plus in there for the fun of it. Let's look at R, that's equal to not 12, but 15, or 0.15. Remember, we've got to work, we'd be consistent with our units, okay? 0.15 meters. And then all we want to do is find out what the force actually is. And hopefully by now you remember Q1, Q2 over 4 pi epsilon 0 R squared. Then we just substitute. So Q1 times Q2 is, so negative 0.4 times 0.7 to give us negative 7/25. Can we just, it's fine, yeah, negative 0.28, obviously. Divided by 4 pi epsilon 0 R squared. So we'll just divide it by, okay, let's put that in 4 pi. Epsilon 0 was 8.85 times 10 to the negative 12 times 8.85 negative 12 times 0.15 squared. Whoops, delete that. Okay. And what we get is pretty big force, okay? We're getting negative 1.12 times 10 to the 11 newtons. So have I done that correctly? Let's just check here. So negative 0.28. Let's do our denominator here. So 4 pi. I mean, this is really small, so I imagine the answer must be pretty big. 4 pi times 8.85 times 10 to the negative 12 times 0.15 squared. .28 divided by answer equals, and there we go. Okay, so we got a pretty large force. Okay, now the direction of the force, well, there's no single direction of the force because they are both they're both causing the force. So the force goes like this, okay? What can we say about the magnitude? We must say they are equal and opposite. Okay, we must say that, okay? And that is because this is causing attraction to this, and this is causing attraction to this. Those forces, the force is due to the interaction between the two of them, and both those terms are up there, okay? So the force must be equal and opposite. If we increase one, that affects the force for both of them. Okay, unless of course we decrease one of them to 0 or increase one of them to 0. Okay, so the next thing is we can also ask about, is this the only attractive force between the objects? It's not, because some objects, if they have mass, will be affected by gravity. What you will see in the task I've given you today is that gravity and the electric force are very, very different. Okay, to give you an idea about how weak gravity actually is. So what I've done, guys, is I've put some past paper questions into the PowerPoint, which I'd like you to go through yourselves, okay? It may be that you spend the whole time actually doing this. I'm also aware that 2 of you have got exams this week, okay? So I don't want you to spend any more time outside of lessons covering this stuff. Artur, you've got your driving test or license, so lessons. So I hope that goes well, whatever it happens to be. So what we'll do is we'll review some of this. What am I going to say? We'll review some of this basically as soon as we can. We'll try and review those tests as well this week, but don't stress about it too much for now because you've got exams of various kinds and various importances. Okay, so there it is.